Welcome back to another statistics video. So in this section, we are going to look at sampling distributions of a statistic. And our goal is to figure out which sample statistics can we use to estimate a population parameter. So we know in the real world it's unlikely that we can collect data from every item in a population. So what happens is we collect data from a sample, and we're asking, if we collect data from a sample, can we use, for instance, the mean of that sample to estimate the population mean? Can we use the median to estimate the population median? Can we use the variance to estimate the population variance? Can we use the proportion from the sample to estimate the population sample, or the population proportion? So that's what we're investigating in this section. So this is a really theoretical section. What's going to happen is we're going to look at just a really small population of 3 items, and we are going to work our way through and figure out which of those, looking at that population of 3, can we collect information about for samples of size 2, and we're going to look at all the different samples of size 2 to estimate a population parameter. So let's get started. When we talk about the sampling distribution of a statistic, we're going to look at all possible samples in the population of a certain size. In our case, our population is going to have 3 items in it, and we're going to look at samples of size 2. So we're going to look at all the different samples. And then we're going to do something with that. We're going to look at a sample proportion. We're going to look at the sample mean, and we're going to say and see, does the sample mean tend to target the population mean? Does the sample proportion target the population proportion? And we're going to start out with the proportion. So we're going to create the sampling distribution of the sample proportion for an exact, for an example. And we're going to see what that's going to look like. So here's what we are going to investigate. And what we're actually going to see is that that sample proportion actually does target the population proportion. So let's consider a population of items 1, 2, and 5, and we're going to select random samples of size 2. So if we were to look at all the different possibilities here, we're selecting samples of size 2, so there's my 2 items. We are doing this with replacement, that's important. So we have 3 options to select that first item. And then let's say we select it, we put it back in the hat to be drawn again. Now we have 3 options for that second item. So there's a total of 9 possible outcomes, but we need to list all the 9 outcomes. So here's our 9 outcomes. We could have a 1 on the first number and then put it back in, choose again, and we could have a 1 on the second number. Or we could have a 1 and then choose a 2, or we could have a 1 and then choose 5. So that's all the possible ways we'd have 1 as that first item. And then we do the same thing with the 2. Let's let 2 be the first item. Our second item could be a 1, a 2, or a 5. And then we could have a 5 as the first item, or a 1, 2, 5 for the second item. So there's our 9 different outcomes. So we're going to look at the sample proportion here. And we're going to look at the number of odd numbers. So if we were to look at this population and we were to look at the proportion of odd numbers. So here's our population. How many odd numbers do we have in here? So in this case, we have 2 odd numbers out of the 3 total. So there's our population information. Now we're going to collect information from our sample, or samples. So I'm going to create a table here. I'm going to list all of these different samples. We had a 1, 1, 1, 2, 1, 5, 2, 1, 2, 2, 2, 5, and then 5, 1, 5, 2, and 5, 5. And we're going to look at, in each individual sample, what's the proportion that's odd? Well, if we look at this first sample, both of those numbers are odd, so we have 2 out of the 2 that's odd. If we were to look at this one, we have 1 out of the 2 that's odd, so that's 1/2. If we were to look at the sample of 1 and 5, both of those numbers are odd. If we were to look at, let me correct that. Is that easier to see? The next sample, 2 then 1. Well, there's one number out of that sample that's odd. Here, we don't have any odds, so the proportion would be 0 out of 2, or just 0. Here, this sample has one odd number out of the 2. This one, they're both odd. In this one, there's one odd number out of the 2. And this one, they're both odd. Now, when I created this probability table, what we're actually looking at is what's the probability that each of these items is going to happen. Well, they all have an equal chance of being selected, so our probability would be 1/9. So if we had all of these in a hat, the probability of each one would be 1/9. Now, we could actually look at this table in a different way. We could kind of reconstruct it, if you will. So notice some of these reoccurring numbers, 0, 1/2, and 1 were reoccurring here. So if we were to look at all of the zeros, how many times did 0 happen here? Well, 0 only happened one time, so that probability would just be 1/9. Okay, but 1/2 happened quite a few times. So 1/2 happened 1, 2, 3, 4 times. So we could add those probabilities together. 1/9, 1/9, 1/9, and 1/9. If I add those, I get 4 9s. And then if we look at all the ones that we have, we have 1, 2, 3, 4 1s. So we would have 1/9 plus 1/9 plus 1/9 plus 1/9. This one's for 0. So the probability of having a proportion of odds as 1 would be 4 9ths as well. So here's our probability distribution, kind of thinking about this in terms of a discrete distribution now. And we could take this table and we could rewrite it this way. So now let's talk about, what does all this mean? Well, let's look at the sum of all the proportions. If I were to add up all these numbers, what do I get? So I would have 1 plus 1/2, 1.5, 2.5, 3, 3.5, 4.5, 5, 6. So I have a total of 6 there, just adding that column up. So let's find the mean. mean of those proportions, well, I have 6, that's the sum. And remember, to find the mean, we add everything up and we divide by how many numbers we added. We added a total of 9 numbers. So our mean is 6 over 9, which reduces the 2 over 3. So remember when we looked at that population parameter earlier? We looked at what was the proportion of odd numbers in that population, and we had 2 of the 3 that were odd. So check this out. The mean of the proportions and the population parameter are the same thing. So what this means, what this shows us, is that this sample proportion actually targets the population proportion. And since that sample proportion does target that population proportion, then we can say that the sample proportion is a great estimator for the population proportion. And that's what we're looking at in this section. Which ones are going to be good estimators for these? And it turns out that if we were to do this in other populations and look at other size, maybe we had a population of 5 items and we needed to look at items of 3. This set would be much bigger, but if we went through the exact same process, then we would end up showing once again that the mean of the proportions does target what that population parameter, which in this case would be that proportion. So let's look at another one. Let's look at the sampling distribution of the sample means. So we're going to use that same set here. There's our 9 different items that we're going to look at. And we are going to construct a table again. So I'm going to look at all those samples. I'm going to look at the mean of those samples. And we're going to look at the probability. This table helps us create a more condensed table like we did before. So the mean, we're going to find the mean for each sample. So we could use StatCrunch to do that. So over here, I'm going to delete that information. So my sample consists of 1 and 1. If I want to find the mean, I can go to Stats, Summary Stats, Column, and I want to find the mean of list 1, Compute. So it says that the mean is 1. And we're going to do that for every sample. So we're going to do 1, 2. And then go to Options, Edit. So I changed this number, but I still want to find the same thing. Press Compute. My mean is 1.5. Same thing with 1.5. Options, Edit, Compute. The mean is now 3. So you can see what we're doing. We're finding the mean for each one of these. And I'm just going to tell you what the rest of these are. This is 1.5, 2. This one's 3.5. This one is 3, 3.5. And then 5. Now, when I talk about the probability, I'm talking about what's the probability that each of these samples happens. Well, there's only one way I could get the sample out of the 9 different options. So the probability is 1/9. The only one way I can get this out of the 9 options, that probability is 1/9. And that's going to be the same for all of these. So notice again, we've got some numbers here in this mean column that happen more than one time. So we could actually write this table a little bit more condensedly. And then look at the probabilities. So we had means of 1, 1.5, 2, 3, 3.5, and 5. And this is usually what MyMathLab's going to want on some of these problems. In some problems, it's going to ask you for both of these. That's why I'm rewriting it this way, to demonstrate that. So let's look at these. Where did our mean happen to be 1? We have one way that happened. So that's 1 out of 9. Where was our mean 1.5? That happened here and here. So that's 1/9 plus 1/9, which is 2/9. So that happened 2/9 of the time. Where was our probability equal to 2? That only happened one time. Where was our probability equal to 3? That happened 2 times. So adding those probabilities together, 2/9. The 3.5 happens twice. So that probability is 2/9. And the 5 happened one time. So that probability is 1/9. So we can create a discrete distribution there. So we're asking, does the sample mean target the population mean? So let's figure that out. Let's look at the sum of all the means. And then we're going to find the mean of that. So if we were to add up everything in this column, that would be the sum. So if we were to add all these numbers together, so you can get your calculator out, plug that in. And when I did that, I ended up with a 24. So now we want to find the mean of those means. To find the mean, we add everything up and we divide by how many numbers we had. So if we add everything up, we get 24. And we added 9 numbers. So the mean of the means is 2.67. Well, what is the mean of the original population? Well, the mean of the population would be 1 plus 2 plus 5 divided by 3, which would be 8 over 3, which is the same thing as what we got above. 24 over 9 reduces to 8 over 3. So you can see how we're getting the same thing here and here again. So what this means is that sample mean does target the population mean, so it's a good estimator. So it's going to be a good estimator for that population mean. So let's look at the next one. Let's look at the sampling distribution of the variance. So we have to recall that the population variance formula is a little bit different. So when we find that population variance, we'll have to use StatCrunch a little bit differently, different option there. So let's do that. So we've got 1, 2, and 5. There's our different samples of size 2 from that population of 1, 2, and 5. And we're going to go through and we're going to find the sample variance for each. So let's list all the samples. And let's look at the variance. variance here would be 0. That's because there's no variation between those. And we could go into StatCrunch and we could show that. We would have 1 and 1. If we go to Stats and Summary Stats, columns, I want the variance. This is your sample variance and sample standard deviation option here. Press Compute. There's no variation between that, so it would be 0. That next one is 1, 2. Compute. Now my variance is 1/2. And then if I do 1, 5, and then compute, my variance is 8. And we're going to do that for all 6. So we had 1/2. And we had 8. So if I do the same thing with 2, 1, I would get 1/2. And that would come just from plugging that in. I've already done that off to the side. You can verify that using StatCrunch. 2, 5 gives me a 4.5. 5, 1, if I plug that in, I'm going to get 8. It would be the same as 1, 5. 5, 2 is going to be another 4.5. And 5, 5 would be 0. If we wanted to create that probability column, we could. Each sample has a probability of 1/9. So notice we do have some overlapping numbers here. 0 happens a few times, 0.5 happens a few times, 4.5 happens a few times. So we could condense that table. And sometimes my math lab will ask for that answer. Let me write 1/2 as 0.5. So we have a probability of 3/9 to get 0, a probability of 2/9 to get a 1/2, a probability of 2/9 to get a 4.5, and a probability of 2/9 to get an 8. And if I add this, that gives me a 1, which means that I have found probability for each. So now let's analyze this. We want to look at the sum of all the variances. So if we were to add this column up, that's what we're looking for there. So if I add all those numbers, I get 26. So now we're going to find the mean of all those. So to find the mean, we're going to take that sum and we're going to divide by 9. And that's going to give us a 2.89. So we want to compare that to the population variance. So to find the population variance in StatCrunch, remember our population was 1, 2, and 5. I'm going to go back to my summary statistics, but I'm not choosing this option. I want the option down here that's unadjusted. That's their way of saying population variance. Hit compute, and that population variance is 2.89. So our population variance is also 2.89. So since these are the same, once again, we would say that that sample variance does target the population variance. So now, since we've done that, let's look at the standard deviation. So the standard deviation kind of bounces off of the variance, right? Because we said that the standard deviation is equal to the square root of the variance. That goes way back to chapter 3. So if I were to recreate that table and put that in here. So here's the table that we had from above. Let's find the standard deviation. All we have to do is take the square root of these. So we've already done the homework, the hard work here. So the square root of 0 is 0. The square root of 0.5, if I were to do that in my calculator, so I'm going to have 0.5 and then do square root. I'm going to use 4 decimal places, 0.7071. 8 and take the square root of it. I get 2.8284. Square root of 0.5 is 0.7071. Square root of 4.5 is 2.1213. 8 was 2.8284. 4.5 and then 0. So there's our numbers. Now notice we did round here to 4 decimal places. We used that variance to get there. We could have used StatCrunch as well. We could have found the variance for, let's say 1, 2. And down here, just choose your standard deviation. There's your standard deviation. So it would be 0.7071. So you could use the variance, or you could use StatCrunch to find the standard deviations. We could also recreate that table. We talked about that before. I'm just going to skip that step here since we've done that several times. Let's see if the standard deviation is going to be a good estimate. So we are going to take the sum of all the standard deviations. So if we were to add up all of those numbers in the calculator, what do we get? In this case, we get 11.3136. So now we need to find the mean of all of those standard deviations. So to find that mean, we're going to take that sum and we're going to divide it by the number of numbers we added. We added 9. So our mean is about 1.2571. So let's find that population parameter. So we could use the variance to take the square root, or we could use StatCrunch. I'm going to use StatCrunch to show you how to do it in here. So there's my population 1, 2, and 5. And I am going to choose the unadjusted standard deviation. That's what StatCrunch calls the population standard deviation. And that population standard deviation is 1.6997. So notice there's some difference here. So even though the variance was a good estimator, the sample standard deviation doesn't tend to be a good estimator. Now, what happens with the sample standard deviation is that that difference tends to be so small, we can tweak the standard deviation. But in general, we say the standard deviation is not a good estimator. It's what's called a bias estimator. All right, now let's do one more. Let's look at the median. You may be wondering, well, what about the median? Because we haven't talked about that one yet. Well, we can find the sampling distribution of the median as well. So there's our 9 samples. So we're going to list all the samples. And we're going to find the median of each sample. Remember, the median is the number that's in the middle. I'm going to create my table. And I want to find the median. So the number in between the middle here the number in between the middle here. And since I only have two numbers, I got to find what's in the middle of those two numbers. The number that's in the middle here. We could also do this in StatCrunch if we wanted to, if you're not sure. We could list our sample, and then we could choose the median option down here. So the median is 3. So StatCrunch will give you the answer, but we could also do it by hand since we only have two values. But if you're not sure, use StatCrunch. So the number in the middle here would be 1.5. 2. The number in the middle here would be 3.5. 3, 3.5, and then 5. So there's our numbers. Now let's look at the sum of all those medians. If I were to add all those numbers up, what do we get? So in this case, we're going to get 24. And now we need to find the mean of all the medians. So remember, to find the mean, we're going to take that sum and we're going to divide it by how many numbers we added. In this case, we added 9. So we've got 24 divided by 9, which is going to give us 2.67. So now let's look at that median of the original population. Remember, our population was 1, 2, and 5. The median's the number in the middle when everything's in order. In this case, our median is going to be equal to 2. So we can see a big difference between these guys. So because they're not the same value, we would say that the sample median does not target the population median. Which means that it is not a good estimator. So we would never want to use the median from a sample to estimate the population median, but we've seen some really good estimators in this section. The proportion, the mean, and the variance are all unbiased estimators because, as we saw in our example, it does target, that sample statistic does target that population parameter. The median and the standard deviation are not good estimators. The range would not be a good one as well. You can work through that one to see that. So in the next few sections, we're going to use this information about unbiased estimators, and we are going to do things like confidence intervals and hypothesis testing with them.